Good afternoon, and thank you very much for having me. Last time I was here at Warwick, it was probably about 5 or 6 years ago, and I was still an academic, and then everything's really changed since then. So last year, I was part of a company. I was a co-founder of a company called D3D, which was acquired by Altair, where I was a CTO. And we had some quite interesting implicit modeling capabilities. And really for the last year since that acquisition, we've been working really hard to implement that technology into Altair and trying to redefine how we approach implicit modeling. And so I'm pretty pleased to announce today and show you how Altair is making implicit modeling mainstream for engineers and designers. Now, what we're going to look at today, in case you don't know, we're going to have a quick look at what implicit modeling is, what are the promises that we should get from implicit modeling, what are some of the criticisms over the years, especially as part of Gen3D. We've seen our fair share of struggles and challenges to use implicit modeling in sort of typical design applications. And then the bit I'm really excited for is to announce and reveal what we've been up to sort of secretly behind closed doors for the last year to get this technology inside Altair Inspire. So, what is implicit modeling? Well, essentially, implicit modeling represents geometry using implicit functions. And you can kind of think of this as a 3D field of scalar values, where outside the surface or the boundary of the geometry, you can have positive values. Inside of that, you have negative values. And between those two, typically where the values are 0, you can imagine that's where the surface is created, but it could be different sort of contour lines, as you can see in the image, inside or outside of the actual geometry. And what this gives us is a very efficient way of describing quite complicated geometry, and you can do lots of operations implicitly that would typically be quite difficult to do with traditional CAD tools. So just an illustrative example, you can imagine something that looks like this, which is just a lattice geometry with 250,000 unit cells, really fine features. And you can imagine if you try and represent this with sort of typical B-rep or NURBS patches, you're going to need something like 25 million patches to represent this sort of geometry, which probably most, if not all, machines or hardware would struggle to represent. But with implicit, it's a single equation. You can trim that geometry. You can morph it. You can do anything you want with that in real time with slicing, and really make use of the complexity that you get from implicit modeling. Now, let's look at some of these promises and criticisms of implicit modeling that we've come across. Now, the promises of implicit modeling is that we should be able to have robust geometry creation and control, where you can create very difficult or complex branching structures, lattice structures, and because we can represent this sort of geometry as fields, we get that basically sort of complexity for free. We want complete spatial control over the geometry. So because we're representing this geometry as a field, we should be able to say at exactly every point in space what the sort of spatial parameters are. So you can get some really fine-featured, fine-tuned control on your geometry. But we can also make use of sort of GPU technologies or parallelized technologies. So implicit modeling is very easy to distribute across a lot of resources, where you can very quickly compute and display these geometries. And implicit functions can be kind of seen as a recipe, which inherently makes them quite scriptable, which makes them repeatable. And you can sort of have these workflows that you could make tweaks and variations on. But also, with implicit modeling, essentially anything can be created as a field, anything can be created as a function, so it's infinitely extensible, where you can really create anything that you want. However, just to bring a bit of balance here, over the years, there's been a lot of promises of implicit, and there has been criticisms or challenges in using that in day-to-day workflows. So, for example, industries and companies have invested heavily in traditional CAD tools and training and expertise, and typically implicit modeling to date has been quite tricky for traditional engineers and designers to use. They're unfamiliar in terms of the workflows. The difficulty in working across different geometry representations, where you want to go from, say, some mesh model or some BREP model or some NURBS model, and go in and out of implicit modeling. There's no construction history. It's not parametric in that way, so it's hard to roll back and make changes upstream, which will then affect your geometry downstream. There's been a big challenge getting implicit geometry out of implicit modeling and linking it up to other tools, such as simulation or analysis. And we typically see a very steep learning curve with the tools required. So typically, how good you are at maths and how good you are at topology and geometry will dictate just how much you can get out of implicit modeling. So that can really be a barrier to entry for a lot of people coming in. And then finally, if you don't have access to the core functions or the core features of implicit modeling, you're kind of tied to what you can do with the user interface and the user experience there. And it makes it very difficult to have niche workflows or niche sort of design applications. So we took all of that on board last year when we decided to integrate this technology into Inspire. And we looked at all the challenges and the promises and the criticisms, and we thought, okay, well, how can we do things differently in Inspire, and how can we address all of these things? And we boiled it down essentially to 5 key points. Now, the first point is that we wanted implicit modeling to feel no different than traditional CAD workflows, make it feel familiar to people who use other CAD tools. So the first thing we did is in Inspire, we have, at the moment, 3 geometry representations. So we've got parametric, surface, and solid modeling with BREPs. We've got the PolyNURBS tools and geometry representation, which is very good for topology optimization. We've got the facet geometry representation, where it could be scan data, it could be just any sort of mesh model. But what we've done is added implicit geometry as a 4th representation type, where we can then easily go in and out between any of these geometry representations as needed. We've also added a dedicated ribbon for implicit modeling. So everything that you can do with implicit is going to be completely contained in its own ribbon, so it's all easy to find, and broken it down into different ways of creating and modifying geometry, just like typical sort of CAD operations. And what we want to do is essentially be able to apply these implicit operations and geometry tools directly to any of these non-implicit geometry types. For example, here's a topology optimized part where we will wrap that with a PolyNURBS surface, so make it smooth. But we can just immediately select that and go to the implicit modeling tab and throw a lattice in there, and then put a shell right around that. We can slice that and see what it looks like on the inside. We can very quickly fine-tune what the lattice is inside of that model. We can then Boolean union that with the non-implicit interfaces and smooth the union between them. We can also take mesh data, could be scan data, could be any sort of mesh model, where again, we can select that, do an offset of that geometry. We can shell it, so with one click, and we can throw up a slice plane so you can see what that looks like, and vary what the offset surface looks like. But what about, changes to the geometry upstream? So you put some lattice or any sort of implicit geometry inside, and you want to go ahead and change what that model was beforehand. So we can apply a lattice with a shell around it onto this BREP geometry, and we can change what the shell thickness is. We can, again, change what some of the parameters are for the lattice very easily. And we can then go ahead and roll back to the BREP geometry, and we can take the sketch plane that we've made previously, and we can extrude a hole through the geometry that we had before we even applied the lattice to it, and then we can cut that out of the geometry, accept it, so you can see that the BREP model's changed, and then we just roll back forwards to where we were with the implicit geometry, and you can see that the lattice is now formed around the hole that we've put in. And we can go into the history and suppress that action, so you can see it immediately updates, and you can unsuppress that action, and you can see that we can change some of those history items upstream and how it affects downstream. Now, there's obviously a lot of parameters that you can change in implicit modeling, and they all vary the geometry in different ways, so we wanted to have a really flexible way of editing and assigning those parameters. So in this case, we can turn that brep interior with a slice plane into some lattice so we can see it. We've got drop downs for different unit cell types. We've got buttons for different types of lattices, for a skeletal or a sheet lattice. We can use the sliders to dynamically edit some of the densities or the volume fraction of that lattice. We can put a value in. We can assign a variable to that if we want to edit it later. And we can also go into a field, so we can toggle the field mode on and create a field in place or use one that we've made earlier. So you can see that we're now having an adaptive cell size in the vertical plane. And we can then, while seeing how that affects the lattice, we can manipulate the field in real time and see what that does to the lattice. And we can also either use the widgets on screen to make it nice and easy, or you can type in the values so you have exact unit cell sizes at each plane. And once you're happy with that, you can go back to your lattice and carry on editing the lattice as you saw previously. The second thing, we talked about GPU acceleration. So we've rebuilt essentially the implicit engine directly onto the GPU. So everything that we can do in implicit is done on the GPU. So we get, as you've just seen, some real-time edits of the geometry and slicing, so you can see inside everything. We've got high-quality rendering of these geometries where we can apply textures and materials and shadows and lighting and scenes. And we can even manipulate the geometry whilst being in this high-quality rendering mode. So what does that look like in practice? Well, we've got some component that we've designed. We can roll back and change the number of fins that was in this component. We can change the structure of that ISO grid that's on the structure, and we can accept that. But we can also slice that in real time, and we can choose different slice planes as you would like. And you can see what that looks like internally. But at any point, we can say, well, why not go into the high-quality rendering mode where we've applied a material to this? And you can apply a whole host of materials to that. So you can have textured materials, in this case here. So we've got a cast material. But we can also choose just how strong that texture is that's being applied to the surface of the geometry. And you can do that in real time. And you can also edit the geometry in real time while still having the rendering mode on, and see how that geometry changes while seeing all of those materials applied. So here you can see a couple of examples of some rendered geometries that we've created. Here's another one. And finally, the third one. So third point, we wanted the field-driven design to be intuitive and flexible. So it's obviously being able to control the geometry at every point in space can be quite difficult to do, but we wanted to make that as user-friendly as possible. So we've made a number of different ways to create and manipulate and apply fields. So you can use reference geometries like planes and axes and points. You can use brep features, faces and edges and vertices. It could be implicit functions themselves. It could be simulation data, point clouds, or even a custom Python script that you bring in and apply to your geometry. So what does that look like? Well, we can apply a field to the lattice, and we can choose either one of the planes, the global planes in the browser. We can click any plane in the viewport, and you can immediately see it change the field that you see on screen. So you can have radial gradients, you can have linear gradients, you can have spherical gradients, gradients off of all sorts of geometries, which you can then manipulate and visualize immediately as you move all of the widgets around. And we can do that for basically any parameter where you see the field icon. So for lattices, that would be things like the cell size and the density. When we do that union, the smooth union with other objects, you can do variable fillets, variable shelling. Anywhere you see that field icon, you can do any sort of field-driven parameter. So we can do linear gradients, as you can see here. And these, again, You can set exact values, you can clamp the values, you can do cylindrical gradients, where you can choose a start and an end point for the radii of the field gradient. Just having a look there. You can do a spherical gradient as well, where you can, again, choose a start and an end radius, where you can manipulate those either by hand or with exact values in the tables. And one of my favorites is you can also assign a point cloud to any geometry. And as you can see here, you can either import that data from a CSV file, you can put them in by hand, you can manipulate those points in space, you can change the value of what the field is at every single point in space, and you can see how that manipulates and edits the geometry in real time. You can even use it with a slice plane, so you can see inside. Obviously, some fields are more complicated than others, so if you want to see what that looks like internally, you can just put up a slice plane. Now, fourth, so Altair, obviously, very rich in simulation tools and analysis tools, and one of those bottlenecks that I mentioned earlier is being able to make sure that the geometry that you're creating with implicit obviously is going to perform and do what you want. So here's an example of a BREP part that has a section with an implicit geometry in the middle. So this is using two different geometry types. And we can do a sim-solid analysis in Spire on this, a structural analysis. So you can get the displacements, you can get the stresses on here, you can get the modes, and you can also even do a full assembly with one component in there that's an implicit part, or actually it's a combination of an implicit with a non-implicit part in an assembly of 20 parts, and run an analysis of this and visualize the results there. You can also send the geometry to the Print 3D model module in Inspire, and you can see what that will then look like in terms of a print simulation, where you can see some of the displacements or any warping that might be needed, so you can then fine-tune the geometry after the fact and make sure it prints. So, if all of those things aren't enough, the next thing we wanted to do was make sure that people could extend the product. So with implicit modeling, if you can do almost anything, but how can we allow people to extend the product to do exactly what they need? So Inspire has a very rich Python API, and we wanted to also expose implicit modeling to all of those Python commands as well. So what we've gone and done is, so far we've got 75 different implicit operations that have been wrapped in Python. For every single one, there's a demo where you can run it live in the product, and it will run, and there's a debugger, a Python debugger as well, inside Inspire, so you can test it and see how it behaves. There's documentation for every single operation that you might need, so you can see exactly which parameters you can tweak in the code and run them, which means that basically anything that you can do in the user interface, you can do through an automated Python script. But it's not just about automating the commands that you can do, it's also about extending the operations that you can do. So we can even have custom equations which run on the GPU as well. So you can write your own custom implicit functions. They will then be evaluated on the GPU, and you can use those downstream just like you would any other implicit geometry. And because it's on the GPU, it will run just as quick as anything else that you did in the software. So to close, well, we're bringing this to Inspire 2023 release coming later this year. It's going to be extremely quick. It's going to be working on the GPU. It's extremely complete, but it's going to be very easy to use. We're trying to make it as user-friendly as possible. It's going to be affordable. It's going to be part of the base Inspire license, so there's no additional fees or anything to use implicit. And finally, we're going to be running a general beta soon. So if you're interested and you want to know more about any of this, go ahead and scan the QR code, and you'll be one of the first to know exactly what we're up to. So with that, thank you very much, and it's been great.